So Professor Newhouse, as a New Englander, went to Colby College. Satellite has got great fishing up there, right? Yep. And that's where he did his, where he learned to love chemistry. He went to La Jolla. He thought he'd get away from the New England winters, and worked at Scripps, where he did his PhD with Phil Barron. And he did his postdoc with E.J. Corey, who's one of the gods of organic synthesis at Harvard. And somehow he just couldn't get away from the Northeast. He loves this weather so much, right? That we were lucky enough to have him join our faculty a few years ago. So without any further ado, join me in welcoming Professor Newhouse.
Thanks, Kurt, for the invitation today. I'm really excited to share some things about organic chemistry with you guys, because the one thing that I like more than fishing is organic chemistry. And so there are several graduate students here who are also going to be sharing organic chemistry with you through the power of several different demonstrations. And so they're all going to introduce themselves now. So if you guys could just come up and introduce yourselves. So you can see that they're being really safe. Alex has her goggles on, and they'll be wearing gloves. Rule number one with science is first of all, always be safe. All right, so.
Hi, I'm Alex. So I got into chemistry because I want to help the world in any way I can, and chemistry is one way to do that. I mean, our drugs require chemistry to make, like say your antibiotics when you're sick. Yeah, so there's just various things that chemistry can help with. And I grew up in Massachusetts, and now I'm here in Connecticut and doing my PhD in organic chemistry.
Hi, my name's Olivia. I'm a first-year graduate student, and I'm originally from Kalamazoo, Michigan. I got into chemistry just as I was a kid. I loved learning about how things worked and just learning more and more details, and I found fascinating about how life works and how chemistry works and how drugs work. But in the end, it's also a lot of fun. I love doing science. I mean, there's good and bad days, but most of the time, it's really fun.
My name's Kevin. I'm originally from Western Colorado. I guess the reason I got into science is I like playing games, and science is essentially like a game, but where part of the fun is figuring out the rules. So on one hand, you're trying to win and get progress in your research and find things out, but on the other hand, you're trying to figure out how things work at the same time.
Okay, thank you guys. So I got into science for really similar reasons, and also including that with science, you really have the possibility to dive into the unknown, and you never know what you're going to find until you get out there. So with science, you get to do things like go into the unknown and ask, what is that, or how does it work? And so the specific area of unknown space that I like to dive into is organic chemistry, specifically the organic chemistry of molecules isolated from nature. So molecules from nature have provided us with several diseases. Like, for example, Alex mentioned that there are molecules that act as antibiotics, and so when we get sick, we can take antibiotics to make us better. Actually, everything from a headache to cancer, there's a molecule that's been isolated from nature that can help with that. Here are 3 examples of different molecules which have different kinds of biological activities. So for example, all the way on the left, this is a structure of morphine. Morphine was one of the first molecules ever isolated from nature. It was isolated about 200 years ago, and it's used to treat pain. And from morphine, we've been able to learn a lot about pain management and also about how pain works in terms of in your body what proteins mediate the pain response. And morphine acts on opioid receptors. They're names for the plants from which morphine is isolated from. Or there's THC. This is the active ingredient that's found in cannabis. And we've learned about cannabinoid receptors from this small molecule. Or there's also a molecule which has become famous recently as a result of Breaking Bad. Breaking Bad, it's now no longer running. How many people have seen Breaking Bad? Just so. Okay, good. I'm glad that some of you have seen Breaking Bad. So Breaking Bad is all about methamphetamine, which is not isolated from nature. It's a synthetic drug. And so that's what we do. We all do organic synthesis. We make molecules like methamphetamine in the lab. And methamphetamine is based on a naturally occurring molecule. So methamphetamine, although in the show Breaking Bad it's blue, it's actually supposed to be white. And actually so is THC. THC is also a white powder. And morphine is all a white powder. And so one lesson here is that not all white powders are the same. And so Alex now is going to, has an impure solid over here.
I don't know, this might be a little hard to see from over here, but there's this blue clump in the middle there. Let's see if we can put it on this.
It's on.
Put it on the screen. Ready? Let's see how well you can see it. I'm not quite sure if it's. Can you kind of see it a little bit?
So see that blue solid in there? That's like Breaking Bad with the blue meth. And then there's also some white solid in there. And what Alex is going to do is Alex is going to remove the blue color by a process called recrystallization. So Alex is going to take this solid and she's going to dissolve it in a liquid. The liquid she's going to use is water. This is a water-soluble salt. So there she is, adding 10 mils of water. It's actually amazing. This salt is sodium acetate, and it is very soluble in water. So you can see it looks like there's tons and tons of this white solid. Look at how little the volume of water is that she's adding. She's adding 40 milliliters, but it's actually all going to dissolve in that very small amount of water. I was really surprised by that when I first saw that. And so now she's going to be, I've lost track. This is the fourth one?
I'm putting 40 mils?
40 mils.
So it's not very much. You can see that it doesn't even look like it's a solution. It's just kind of, still kind of looks like a bunch of solids, right?
And so now Alex is heating that up. And we're going to come back to this solid because it takes a little while to dissolve. But over the next 45 minutes or so, you guys will be able to see some of that. So the structure of molecules determines their function. I just showed you 3 really different structured molecules which are isolated from nature that all have really different functions. But here are several different organic molecules. These are called alkanes. They contain only carbon and hydrogen. And there are a different number of carbon atoms, and depending on the number of carbon atoms in the molecule, their properties are different. And here are the boiling points and the melting points for these different molecules. So the boiling points range from negative 162 degrees Celsius, that's really cold, all the way up to 174 degrees Celsius. That's really warm. And if you look at the molecules, some of you might be thinking, well, they all pretty much look the same. I think that that's fair. These are all very similar molecules, but their structures are slightly different. They have a different number of carbon atoms and hydrogen atoms, and the different number of atoms lead to these different properties. And it's not just boiling point and melting point that vary in response to the structure. So if you can take, for example, all of these petroleum products. There are petroleum products with different numbers of carbon atoms. All of these things are isolated from the ground. And so we use these petroleum products for different functions. So for example, what do you use gasoline for? Anybody? Cars. Yes, that's right, cars. Okay. How about some of these other things, like asphalt? Oh, yep. Roads, yes. Isn't that amazing? So petroleum products both go into cars and are for the roads, which just blows my mind. And the only difference is the number of carbon atoms. Or for example, who knows what's in a kitchen stove or a grill, a gas one of those? Propane, nice. How about a lighter? Good, I'm glad nobody knows about that. Okay, so the number of carbon atoms determines the function of the molecule, and so the structure determines the function. And we use these different chemicals for different things. So what else more specifically with regard to gasoline, what do we use it in a car for? Yep. What's that? Driving, yes, that's right. What else do we use the gasoline for? For combustion, yes. So what we do is we combust the gasoline. And one of one of the things regarding gasoline combustion, or actually combustion more generally, that was determined by Elizabeth Fulham was this concept of catalysis. So she wrote this essay on combustion that was written in 1794. That's a long time ago. And that's when the concept of catalysis was first introduced. She actually had some choice words to say about some of her colleagues. And so I don't know if you can read this text. It's in this very old script, but she says that why she went into science was that it kept my mind, led me to do this mode of amusement, which I found entertaining. So she found science fun and entertaining and amusing. And so here are the choice words about her colleagues. She says that her colleagues are chilled with horror at the sight of anything that bears the semblance of learning in whatever shape it may appear. And should that specter appear in the shape of a woman, the pangs which they suffer are truly dismal. So apparently, her colleagues were really upset that she was a woman and studying catalysis. So I thought that was pretty interesting to share. So catalysis is also used to increase the octane rating in gasoline. So there's a process that was developed in the early 20th century, and it's known as the Howdry process, which increases the octane rating of fuel. And actually, the Allies in World War II had gasoline that had an octane rating over 100. And so they had about 20 points higher on their octane rating than the Nazis. And so that led to an advantage in airplane combat that led to the Allies having planes that were faster, could carry more weight. And so all of a sudden, the Allies won World War II as a result of the Howdry process and improving the gasoline octane rating. So one of the things that can happen with a catalyst is that molecules can combust very quickly. So here's a chemical formula. The first molecule, this is methanol. The next one is oxygen. And then those are converted to water and carbon dioxide upon combustion. And while this can occur very slowly, it can also occur very quickly with a catalyst. Or it can occur very quickly with an ignition source. And so here's ethanol. Ethanol has a very high octane rating. What's the octane of gas that you can get at the gas store? It's not a gas store. Gas station. 93? Yeah, you can't. Yeah, look at this. Man, so in race cars, they use toluene. Look at that, 121. Pretty nice. Or this is why they add ethanol to the gasoline in some places, especially in the Midwest, where they have a lot of corn. The octane rating is higher. It's 109. And all gas, it's unleaded gas. Tetraethyl lead, it's bad for the environment because the lead is bad for the environment. But it increases the octane rating in gasoline as well. That's been banned for a long time. So we're going to do a demonstration now for combustion. Kevin is going to show you what happens when you take methanol and add oxygen and an ignition source. So we're going to make water and carbon dioxide. So here's Kevin. He's pouring in the methanol into the reaction vessel. We're going to use this plastic container to do the chemistry. Let me just get some goggles just in case things happen here. So he's shaking up the methanol, and the methanol is vaporizing inside and becoming a gas. So there'll be a lot of gaseous methanol dissolved in the air. Now he's pouring out the excess methanol. All right. And now he's going to uncap it and ignite it. Ready? Woo! You guys see that? Yeah. That was combustion right there. Okay, let's do it again. Maybe so it's easier to see. Maybe we'll just do a bigger one. Yeah. Yeah. Yeah, let's do this again. So we're going to try to combust two different alcohols. Methanol is an alcohol. First, we're going to do methanol. Methanol combusts really quickly. So it makes a really big flame. And then we're going to do isopropanol second. Isopropanol is more slow, and so it's harder to see. You just saw methanol, though. So now Kevin's carefully measuring out the volume of methanol. Can you guys in back see it if it's down here, or should we put it up on the counter? You guys can see? Okay. On the counter, okay. You put it up on the bench. Maybe we'll move these ignitions, or fuels for the ignition. Whew, this is still warm.
And so just like in the engines of your car, making sure that your fuel is in the vapor stage is very important for the ignition process because of this ratio of surface area to volume. Does anybody know what the ignition source is in a car?
What's the ignition source in a car?
Compression.
Compression, that's right, compression. So octane rating is a measure of how easily molecules combust in response to pressure. Okay, so this is methanol. This will make a bigger flame than the last one you saw because it's a bigger volume, and we're going to combust a larger volume of methanol. Actually, if you take a look, there's really not much methanol in here at all. I mean, imagine we could fill this whole thing up with methanol. We're not going to do that. But take a look. You can barely see the methanol in there. And now Kevin is going to combust that. That was pretty good, huh? You can still see the flames. Yeah, that was a good one. Nice, Kevin. So you can see combustion releases a lot of energy. And so that's how we move cars through space with fuels. So that was methanol. Now, isopropanol has additional carbon atoms, and the combustion isn't as exciting. So now we're going to do that one. So try to remember what methanol looks like. And now as you watch isopropanol, you'll be able to see some differences because it's a lot slower. It's not as loud. It doesn't make that. It's not as loud. It's not as much flames. It's not nearly as exciting. Maybe we should have done it first instead of second. But you saw the exciting one with a lot of energy released very quickly with methanol. So Kevin's measuring out the isopropanol. How many milliliters, Kevin? 40 milliliters, okay. So the procedure is the same. He's going to add just 40 milliliters. That's a little more than an ounce. It weighs probably about 30 grams or so. And just that very small volume is going to be what's in here. So he's vaporizing it again, like the car engine, right? And then you'll see how slowly this ignites. And we're going to make sure that everyone's paying attention right before he lights it because I don't want you to miss it. It's pouring out the excess isopropanol, so it's only the isopropanol and the vapor. Okay, everyone ready? Okay, don't blink. It's kind of quiet, this one. I don't want you to miss it. Okay, everyone paying attention? Woo! Yeah. So did you see how much slower that was? Okay, that was a bit of an April Fool's joke. So it also does, the combustion of isopropanol is also rapid, but it is slower than methanol. So there you have it. Okay. So one of the products of combustion is carbon dioxide. This molecule up here is carbon dioxide. The carbon is in the middle, and there are two oxygens in red on the ends. And one of the things that carbon dioxide can do is it will move when it's exposed to light. So light in the infrared region will make carbon dioxide move, and it moves in these different ways, in symmetric and asymmetric ways. And we can measure that. And what happens is, so you have a gas, gaseous CO2, that's produced from combustion. So from our cars or from chemistry demonstrations, we make carbon dioxide, and then the light shines on the carbon dioxide, and then the carbon dioxide moves around. And all that movement is then released as heat. And so one of the things that's been happening over the last 150 years or so since industrialization has occurred is we've been doing a lot of combustion. So we drive a lot of cars, we use a lot of energy from our lights, and what happens is now we're releasing all this carbon dioxide, and you can see this is a graph where on the x-axis there's time, and on one of the y-axes there's carbon dioxide temperature, carbon dioxide concentration, and on the other y-axis there's the global temperature. So you can see it used to be colder, and now it's warmer. And as the temperature increases, that's correlated with the concentration of carbon dioxide that's in the atmosphere. So we can measure the amount of carbon dioxide that's in the atmosphere. And the reason that it's warmer now because of carbon dioxide is because carbon dioxide is a greenhouse gas. It absorbs the light, it moves around, and then releases the energy in the form of heat. So that's one of the consequences of combustion is global warming. Now, global warming doesn't mean that it's always warmer everywhere. Okay, so this is a map of the world that shows the temperature in February of 2016, so a little over a year ago. And you can see that it was really warm in Russia in February relative to the average temperature. At the same time, it's really cold in China. And so global warming doesn't mean that it gets warmer everywhere. It means that in some places it'll be warmer, in some places it'll be colder, but overall it becomes a lot warmer. So you can see there's a lot of pink indicating the warmer temperature. So if next winter or this summer it's colder, that doesn't mean that there isn't global warming. It just means that the temperature of the place that you're in is colder. And that's it. So that's all I wanted to point out about that. Okay, more back to organic chemistry. Organic chemistry provides us with all kinds of things, aside from combustion and heat. Organic chemistry is the source of plastic. So there's plastic everywhere. I mean, we have this water bottle. There's one kind of plastic. Oop. It's really soft. Or we have this up here, this cart, which is really hard plastic. And these plastics are made of different materials. And Alex right now is going to make a polymer, which is what plastics are made from. So she's taking two liquids. There are two different materials dissolved, and she's mixing them together. Can you guys see okay? Okay, good. What's that? So mixing two liquids together. You're about to see one of the hallmarks of a chemical reaction. She's going to mix two liquids and get a solid. So anytime you mix two liquids and get a solid, that means there must have been a chemical reaction.
Sorry, I have to do this slowly. If they mix, then so the polymer is going to form on the surface of the two layers, and these two liquids are two different densities, and they don't mix together, which means one of the liquids is water, is going to be on the bottom, and the other one is going to float on the top.
I think, even before the chemical reaction, this is already pretty cool that we have these two different layers like that.
This bottom water layer, and then the top one here is hexane, which is a lighter type of liquid, so it's floating on top of the water. Like when you see oil and water, how they don't mix together?
Yeah, like salad dressing.
Can you put it on the overhead by any chance?
Yeah, we can project this.
Thank you.
Alex, could you bring it over to the doc cam?
Yeah.
No solids inside the flask, right? No solids inside the flask. It's practically magic. So the two layers are mixing, and there are chemicals in the water layer and chemicals there's a chemical in the water layer and a chemical in the organic layer, and they're going to react.
So right now it's a very thin layer, and so it's hard to pull it out of the.
Oh, what have we here?
So I formed a little. So there's a little chunk forming on the surface here. It kind of looks like glue.
Ooh, what's that?
All right, so
Oh my
here's a
God.
little bit that formed.
Whoa.
It looks like kind of like glue. And so what's going to keep happening is, because this is such a large flask, it takes a while for it to make a thin film on the layer, and what would be good right now would be some tweezers to try to pull it up. But you can see here that there's this like glue-looking material that formed on the surface. And so you have one chemical on the top layer and another one in the bottom layer, and they're coming together at the surface, and they're making a new chemical, which is a polymer. Which is
There you
like
go,
plastic.
folks. Two liquids just made a solid. So, okay, so Alex is going to make some more nylon over there, and we're going to carry on with plastics. So on the plastics that you have, there's a number with a triangle around it, and the number indicates what kind of plastic it is. So for example, maybe you guys even have something with you that's a number 2, or maybe you have something that's a number 4. And so these numbers are indicative of the structures of the materials, of the polymer. So for number 2 is known as high-density polyethylene. So this is a polymer which doesn't have a lot of branches. It's just a long, snaky molecule. And those long, snaky molecules can pack together really tightly. And so it ends up being very high density. But low-density polyethylene, this has that same snake, but it has these other strands of polymer coming off of it. And so that's known as branching. And that branching makes it harder for the polymers to stick together, because all the branches get in the way of one another instead of being able to come really close to one another. So that's known as low-density polyethylene. And low-density polyethylene, number 4, is a thinner, softer material. So for example, if any of you guys have a peanut butter and jelly sandwich or something in a plastic bag, that's number 4. Whereas ethylene, if it's made into a high-density polyethylene polymer, then that's something like a canoe or something really hard plastic, like maybe this cart is number 4, I don't know. So close packing is disrupted by branching, and that leads to different densities. So we just saw the 2 different liquids. There's the high-density one on the bottom and the low-density one on the top. There's a high-density and low-density liquids. And with plastics, they also have different densities. So there are all kinds of polymers. So chemistry, through organic synthesis, can lead to all these different plastic materials. So here are some examples where we have number 1, 2, 3, 4, 5, 6 different kinds of plastics. And so for example, we can polymerize ethylene in different ways to get different kinds of plastics, or we can change the molecule structure that we polymerize. So molecules with different structures end up having different properties, and those different properties are used for different things. So structure determines the function. And this is PVC. Maybe at home you guys have PVC pipes, or you've seen PVC pipes places. And that's made from having this halogenated ethylene molecule polymerized. That leads to different properties. This is one of my favorite materials, neoprene. This is the stuff in wetsuits that is really flexible but also really stiff. And that's made from the polymerization of 2-chlorobutadiene. Also, there are polymers in nature too. So for example, rubber tires, those are made from rubber plants. Rubber plants make polymer. And what rubber plants do is they polymerize this molecule here. And so we use this polymer as inspiration for making other kinds of polymers. We change this where it says Me, that's a carbon atom. That's just a specific kind. We replace that carbon atom with a chlorine. So the carbon atom with 3 hydrogens attached to it, a methyl group, is replaced with a chlorine. And as you know, a wetsuit and your rubber tire on a car are totally different materials, and we use them for totally different things, even though there's just this one substituent that's changed. I think that's pretty amazing. So there are other kinds of there's other kinds of branching in materials that leads to different properties. One of my favorite examples of this is the difference between olive oil and butter. So butter is a solid at room temperature, and then when you heat it, it becomes a liquid. But at room temperature, or on a cold day in April anyway, it's a solid, whereas olive oil is a liquid. The reason for this is because of the different kind of chemical that makes up butter and olive oil. So in butter, you have a lot of this saturated fat. And saturated fat is really long and linear, a long linear snake, just like with the polymer, and it can be packed together really tightly. And because it can be packed together tightly, the density is higher, and it's a solid. Whereas olive oil, it has a lot of these kinks. So you can see that the fat is bent. And there's this kink, and that functions like branching does. So it's harder for these molecules to pack together, leading to a lower density and the liquid nature of olive oil. Also of note is that these molecules and these different properties lead to different health effects. And so while the jury is maybe still out on whether olive oil or butter is the healthier of the two, they lead to there are different consequences as a result of these. Something else I wanted to mention about the properties of organic molecules are these really amazing materials like buckyball. Who's heard of buckyballs before? Yeah, buckyballs are really cool. They won the Nobel Prize in 1996. So this is known as a zero-dimensional particle. So it's just a point. Even though it's a ball, it's really just a point. So it's 0 dimensions. And then who knows what this second one is? Just yell it out. You can yell it out. Yes, carbon nanotube. That's amazing. That's a one-dimensional molecule, so it moves like a line. Okay, how about this one? This is less famous. This is a newer material. Oh, geez, graphene. You guys are great. So this is a two-dimensional material. Graphene, it's actually pretty incredible. Some of you guys might have heard this story, but the way it was synthesized is by taking a pencil and then rubbing the pencil on a piece of paper, and then taking Scotch tape and putting the Scotch tape on top of the pencil marks, then peeling it off, and that makes graphene. So anyone here could have done this at home and then won the Nobel Prize, okay? So the next time you're coloring on the walls or doing something like that, just tell your parents that you're working on a science project, okay? So what do global warming, plastic, and healthy food all have in common? Any guesses? In front here. I think she's consulting with her neighbor. Maybe someone else want to take a stab at this one? In front? What is it? Yeah, global warming is on Earth. Plastic, humans make it from Earth. And then healthy food, this comes from the Earth and humans. Okay, someone else? Carbon. Yeah, carbon is at the source of global warming, and plastic and healthy food. These are all organic, all have organic phenomena. I agree 100%. Another one? Organic molecules? Yes, organic molecules. I'm an organic chemist. I love organic molecules. It's no surprise. Oh, we got more? More things in common? They all have to do with chemistry, yes. I like that answer. I agree 100%. More? We got more?
They're all things you studied.
These are things that we study. That's true. Yep. They all affect the environment. Yeah, these are all great answers. These definitely all affect the environment. There's something else that they all have in common. the other thing that they all have in common is radicals. And so in terms of plastics, one of my favorite radical reactions is the polymerization of tetrafluoroethylene. This was actually an accident that occurred. So Teflon, you know that really slippery material on a pan, on a non-stick pan, that slippery material, that's Teflon. And that material is a polymer made from the polymerization of this chemical, tetrafluoroethylene, by a radical chain reaction. And tetrafluoroethylene is a gas, and there was this cylinder filled with tetrafluoroethylene, and there's a scientist who opened up the cylinder to let the gas out, and then nothing came out. But the scientist just moved the tank around and knew it was really heavy and was like, there's something in here, but there's no gas in here. And then put it on a scale, weighed it. Yep, it's definitely a full cylinder, but there's no gas. What's going on here? So then the scientist sawed the gas tank in half, and inside there's this white powder, which was the Teflon. And so that's how Teflon was discovered. It was a serendipitous discovery. Science is filled with accidental discoveries like that. And now we use this material for things like Gore-Tex and spacesuits in addition to the non-stick pans, like this Happy Pan. What's that? Yeah, it's a happy pan. Why is that a happy pan? Because it's easy to clean. Yeah, and that makes you happy. Yeah. Next time you're asked to wash a pan and there's all that food crusted on there and you're trying to wash it, think back to the happy pan and how much happier you would be if you were washing that pan. Or maybe you have a non-stick pan, probably do. Okay. So moving on to chlorofluorocarbons and ozone depletion. So here are pictures of the Arctic, and in red, this shows a high concentration of ozone. So that's the ozone layer that protects us from the sun. And you can see in 1970, there was a lot of red there, so that means there's a lot of ozone. And then later, in the 70s, less, 1980, less. And then here we have 1997. Blue means there's very little ozone. So you can see there's a lower concentration of ozone in 1997 than there was in 1971. And the reason for that was that we were using these chemicals that reacted with the ozone layer and depleted that ozone. So these were the chlorofluorocarbons. For example, one made from tetrafluoroethylene and chlorine makes this CFC. So these chemicals are banned. Their use is banned because they deplete the ozone layer. And since we've banned them in the 1990s, we can now see that there's more and more ozone coming in. And so you can see it goes from red, the red decreases, to blue, less ozone, and then more ozone, and now there's not really a hole present anymore. So we've repaired the ozone layer by banning CFCs. So that was, I think, a pretty good decision to make. And so here's the chemical process that involves radicals for how CFCs react with ozone. We got a question up front here. Yep. That's a really great question. How is it that the ozone reacts with these chlorofluorocarbons? So what happens is we use these chlorofluorocarbons on Earth, and then they vaporize and go up into the atmosphere. And they get up into the atmosphere where the ozone layer is, and you have the chlorofluorocarbon and the ozone. And then light comes in, and the light reacts with the chlorofluorocarbon, and then that makes something very reactive. Once the light energy comes in and hits that chlorofluorocarbon and breaks one of the bonds of that molecule, it makes something very high energy. And that high energy species then reacts with the ozone. And that's what's written up here, where you have this radical, which is the high energy compound, reacting with ozone to make oxygen. And so that's the depletion of ozone. Great question. It sounds like we might have a chemist in the making over here. Okay, so radicals are also involved in healthy food. So there are, you might have heard of free radicals. Free radicals are bad in terms of aging, and actually my laboratory studies free radicals, and we study how to prevent the formation of free radicals, because that's important, may be important for treating various neurological diseases. And there, in the food that you have, like for example in wine, there's resveratrol, or there's this chemical, this is a vitamin, which is found in makeup. Or in blueberries, you have these molecules, which here's an example of one that's shown here, that reacts with the free radicals and prevent the free radicals from hurting you. So there are these various foods and wine, although there's not very much resveratrol in the wine, or in makeup that protects you from free radicals. And my laboratory is interested in making molecules that could protect you from the free radicals your body produces in response to aging. Okay, so now we have an experiment that involves oxygen, like the oxygen that's produced from the ozone layer depletion, reacting with an organic molecule in a liquid. So Olivia has a demonstration where she's going to show you what happens when a molecule reacts with oxygen and light to make another molecule. So the structure of molecules determines their function. It also determines their color. So molecules with different kinds of structures have different kinds of colors. So Olivia is going to show you a chemical reaction right now.
Sure, so we have 3 different reactions. The one he shows up there is the last one. I have 2 other ones. So as he just said, in these flasks, we have these solutions. And what do you guys think? There's also stuff above it. What is that? It's just air, right? And so in air, there's oxygen, which we breathe. So the air is actually going to react with what is in the solution. Can everyone see okay? And so all I have to do is, everyone see what color this is? It's kind of like this clear, I don't know what color.
Pale yellow?
Yeah, yellow. And then I just shake it.
Whoa! It just turned blue, didn't it?
It just turned blue.
What just happened?
And then, yeah, what just happened?
What just happened?
Yeah. Yeah, oxygen. Right, exactly right. And so what happened is the solution there reacted with the oxygen and it turned it blue. And then I think if I leave it for a while, it'll actually go back to clear. So I don't know.
Oh yeah, it's doing that right now.
Yeah,
Color's
right
going
now.
away.
Do you see it? The blue already went away.
So there's another chemical in there. So you added oxygen and it reacted and made it blue, right? So we put another chemical in there. We put glucose in there and some base. And so what happens next is that then reacts with the blue color dye and it turns it back to clear. So first you oxidize, which is when you add oxygen, and then when it goes back, it's called reduction. So then you reduced the dye back to the clear color there.
All right, let's see another one. Olivia.
Yeah, let's see
What
another
else you got for us?
So this is another example. What do you guys think will happen if I shake? Color change? No color change? Yeah. All right, let's see.
Ooh,
That was
nice.
pretty cool.
That's a nice color, pink.
Yeah. And then the same thing as Alex just said. So what we did is we took oxygen from the air in this flask, added it into the solution, turned pink. And if I let it go, the other molecule will then reduce the oxygen. Oh, can you see?
Yeah, color went away.
Yeah. I'm going to shake it because I like that pink. So this last one is what Tim has on the board. It's pretty cool. We can actually get 2 reactions out of it. So it starts, it's called stoplight reaction because we have yellow to red to green. So here when I shake it once, this is nice red color. Do you think, guys, I can get it to change again if I shake it more?
Yeah.
We got some believers here.
Yeah, let's add some more oxygen.
Whoa. Oh my God.
It's really cool. And just, this is the same thing as the other ones. This one can just go to another state. You're adding oxygen again. And then look, it already is going back to red. And it'll
Wow.
actually fade to yellow if we just leave it. So,
Okay. That was really cool. So now we're going to go back to our first experiment, the methamphetamine experiment. We're addressing why is the methamphetamine in Breaking Bad blue? So who remembers from the beginning? Why is the methamphetamine in Breaking Bad blue? All at once now. Yeah, it's not pure. That's right. Okay, so then Alex did this demonstration.
So I have some bad news. You guys are going to stick around a bit longer after the raffle. So right now it's still very warm, and because it's warm, the solids don't want to come back out of the solution. But once I cool it, that's when they are going to want to come back out of the solution. So at the moment.
So here you go. Science takes time, folks.
Oh,
all right?
actually, no, it is happening already. Here we go. We got some crystals growing. There we go. I don't know if you can see in this light. Some
Yeah, we got
crystals.
we just
They're
made
very-
crystals.
All right, let's see. Can we see it in here? If I turn it sideways, maybe? Here, I'll do it from here. Let's see.
Do you see the shards?
Isn't that cool?
Well, if you can't see it and you want to come down here afterwards and just take a peek, you can feel free to do that too. It's kind of difficult to see through here. But you can see that they're forming nice white crystals and the solution stays blue. So you're removing the blue from the crystals. And so we need to do things like that so that we make sure that the drugs that we put in our bodies are pure. So when you get, say, medicine from the doctor, they have to do some purification method, and this is one way to do that. And similarly, if you couldn't really see this from back there, you can see that there's a lot of solids in here now, so a reaction did occur.
So after the raffle, you guys can come up and take a look at these demonstrations, and you could even make some nylon yourself, maybe. So now we just want to close by saying thank you all for coming and for listening to us talk about what we love.